clingman here blocking them up. Can't remember this.
That's fine. Thank you so much for the introduction. I can't remember the title either, so don't worry about that. I'm going to talk a little bit before I talk, and the thing I want to say is that, you know, there's a lot of detail in this, but there's not necessarily a lot of detail in the talk. This is a choose-your-own-adventure style talk, and I want to tell you things that you find interesting and that you can take away from this. So please, interrupt's the wrong word. You'd be doing me a favor by pointing out things that you think are cool or want to hear more about, or interacting with me in any way. So yeah, please let me know how things are going. It's also been a long time since I've given a board talk, and I'm happy to give a board talk, and that's a lot of fun, but that could also be potentially dangerous for you. But to celebrate, I decided I'd make a table of contents. So here's what we're looking at today. Okay, so we're going to try get through most of this, but we don't have to make it through all of this. In particular, this is bonus, and we'll see how that goes. So as a warm-up, I'm going to tell you a one-dimensional story. And hopefully the various bits and pieces look familiar, if not sound familiar, and we'll work through that. So the background for all of this work was that a year ago or so, I was up the hill at MSRI, and some Infinity 2 people, that's maybe an adjective about their work, not themselves, were thinking about how to do limits. Limits are cool, we all like limits, we need to know stuff about them. And the playground for Infinity 2, if you can believe it, is two-category theory. And so the questions were, what sorts of things are true about two categorical limits? And the answer turned out to be, well, maybe nobody really knows. And so this work evolved from something that I consider to be low-hanging fruit in two-dimensional category theory. And through this talk, I hope to convince you that there's still plenty of work to be done in the right-associated version of two-category theory. So we're interested in doing category theory that happens to involve two dimensions instead of the theory of two-dimensional categories. So that's the motivation, and I guess the slogan for this first section, or for this whole talk, is that properties of objects, when we think categorically, are often formulated in terms of representations. And we're going to warm up by trying to understand that. And this should, by the end of the section, you should feel strongly about what it says on the DC license plates and taxation without representation. Not a good joke. All right, definition. So a presheaf is a functor from the opposite of some category into the category of sets. And by a representation of a presheaf, I mean a pair of an object, I, in the category, and a natural isomorphism, rho, let's see which way I decided, from the hom into that thing to F. And hopefully this feels a bit familiar. So as an example of this slogan, I'm going to quickly define vaguely what a limit is. So something we're interested in studying in category theory, limits. So given a functor like this, we say that a limit of f is a pair of an object L in C and a natural transformation from the constant functor at that thing, such that some particular thing such that that particular natural transformation is an isomorphism. And this is, I hope, the usual definition of a limit. So this looks like a representation, except it's not literally a representation because we've asked that some particular thing implements an isomorphism instead of just asking for any old isomorphism. But there's a theorem that relates these two, which I'm going to boldly call a fact, which is that limits of f are in bijection with representations of this other thing. Okay, there's a little bit of work to be done there. But this is a first example of what I mean when I say that properties of an object are formulated in terms of representations. Now there's another one. I'm not going to recall what an adjunction is, but assuming some familiarity with that, a right adjoint to L from C to D is the same thing as a family of representations of these functors. Okay, this is not by definition, there's some work to be done here. But nevertheless, we can pick out at least two interesting things in category theory and phrase them in terms of representations. And there are more, I want to convince you, but we're not going to do that right now. So why are we interested in this? Well, it turns out that we can say something very nice about representations. Representations themselves can be reworked to be objects in some very particular place. And the way that I want to view this is through the following definitions. So given a functor, a presheaf, we say that the category of elements written LF is defined to be a certain slice or comma category, I guess, which, if you like, is defined to be a certain pullback. Okay, and this is kind of the usual thing that we do. So this category of elements has as objects. This is the category whose objects are functors and whose morphisms are natural transformations. I'm happy to change this to anything more palatable. But later on, there are many flavors of this, and I don't know what to write. So sure. Right, so the objects here are things that look like pairs of objects C in C and objects, that's for later, points in the set F of C, and the morphisms between Cx and C prime X prime are morphisms which I'm going to very suggestively draw like this for later, which make this triangle commute. Yeah, thanks. This is inclusion, I guess.
Star goes to star.
Right, sorry. This is not a category. Thanks. That's an important, that's a mistake. So this is star times f. Okay, any questions about this?
Sorry.
Yeah.
This is D.
Where, sorry?
Right there.
2? Oh, right, sorry.
Oh,
So this is the free living arrow, the category I will schematically draw like this. Sorry, thank you. I took that for granted. I shouldn't have done that. Anything else about the category of elements? Okay, why did I do that? Why am I doing any of this to you? Well, there's one more thing that I need to define before I can say why we're interested in representations. And that last thing is what an initial object is. But I'm going to say it in a way that is purposefully unfamiliar. So we might be used to saying something like I in C is initial if C, out of the way, if this thing, I guess, is a bijection for all objects X. That's the usual definition. But I'm going to purposefully make this look strange by instead saying that when we form this particular common category, and once more, when we form this common category, I want this functor to be an isomorphism. So this functor is the thing that sends, so the object of I over C are pairs are pairs C, object of C, and a map to C. And the morphisms are things that make those triangles commute. And by asking this for this projection functor to C to be an isomorphism of categories, in particular it's a bijection, we're asking for it to be a bijection on sets, which on sets of objects, which means for a given C down here, so this is sent to just the object C. For a given C, there is exactly one morphism like this. And the other thing it picks up is that there's nothing else going on. If we draw an arrow in C, automatically that commutes with these arrows over here. So that's maybe an uncomfortable definition of what initial is, but that's the idea. Any questions about that? So the reason I'm kind of dragging us through all of this is because later I'm going to want to start putting 2's in front of everything. And we need to be very careful about what we mean. And it helps to have some kind of very categorical way to sort this out. Yeah?
So I guess you're alluding to the fact that the idea of representation has to do with certain appreciators which we can identify with their category of elements. And that's how we can rephrase like universal properties in terms of comma.
Yeah, I think you're doing my work for me. So yes, that's exactly what we're going to say now, which is the thing that I want to call the representation theorem. And a bit of bad board management has put me in a tough spot. But presumably everyone's done looking at that. So with everything that's presently on the board, we have enough to say, or more or less, the representation theorem. And it has the following to say. It says that given a functor C op to set, the following are equivalent. 1, there is a representation, so of f, or 2, there is an initial object the other way around in the category of elements of f. And I think this is pretty cool. So looking at these facts, we can shift things around a bunch. We can say that, well, we want to work out what a limit is, so it's a representation of this, but we don't know, I mean, we want to compute this ultimately. That might be difficult. That's no much better. But hang on, here's a very concrete formula. Here's a place where we have to look to find an initial object, and we can do that. And the same thing for junctions, and I want to convince you that by combining this and this, we recover the classical characterizations that we have that says, and I'll write this down in a second, that a limit is a terminal cone in the category of cones. It comes out of this plus this. Or that an adjunction is given by universal arrows. It comes out of this plus this. And so somehow this is the thing that's really going on when we think about representations. Yeah? Is that a question or a stretch?
I do have a question.
Okay.
So 2, there's isomorphism as a unique initial object.
Okay.
And 1, it's not obvious that there's a unique, like, it seems like 1 is data, 2 is property.
Or was it ISO, right?
Sorry. That is true.
Yeah, that still doesn't, I think, help necessarily. Although I guess
So
between any 2 of those, by Yonita, there's a unique isomorphism.
that's exactly right.
Okay, great.
So the thing that David is noting is that, you know, this is just an object, and by initiality it's defined up to isomorphism. Well, the same thing happens over here. If we have 2 competing representations of the same functor, the underlying objects become isomorphic, and the natural transformations agree under that isomorphism. So these really are the same. And I might indicate briefly how we would pass between these 2 things, and it is very Yoneda-like, and if you find a way to make this a corollary with the Yoneda lemma, let me know. But in principle, the thing we do over here is the only thing we can do. We want an object of the category of elements, and the way to do that is we already have a candidate object, so we need something in f of I, and we can do that by defining our object to be I, and then rho I of IDI. And this is kind of the only thing we can do, and it turns out to be correct. I should say this is right, how the proof goes, but very far from the proof. And conversely, to add more arrows to a board full of arrows, if we want to go the other way, we do the same kind of Yoneda thing. So given just this data, we need to define a natural transformation from this to this. And the way we do that, inevitably, is to say, well, if we want to know what rho C of an arbitrary morphism f is, we're going to just go around the other way of the square. So we had IDI over here, and we know how f acts on f, and we know we have I over here. So we're going to define rho C of f to be f of I. And it turns out that makes a natural transformation. And then the isomorphism part comes from the fact that this is initial somehow. This is very vague, but I'm happy to elaborate on this if there's interest. Yeah? No, there's no interest. Okay. So that's well, I have one last thing to do when we're done with the warm-up, but I'm happy, any questions about this? All right. So the last thing I want to do is just kind of manually glue these together for you to show you the sorts of things we're going to be looking for in dimension 2. And the manual gluing I have in mind is the following corollary. I don't know how to spell this word. Is that about right? Yeah. Of this? Yeah, maybe after the talk. Right, I think this is an acceptable spelling. So L lambda is a limit of f if, and by this fact, we say that, say L lambda is a representation of this thing. If, by the representation theorem, L lambda is initial with in the category of elements of this thing. And then we have one last isomorphism, which says that this is isomorphic to what we expect it to be. And so if L lambda is initial in there. And this is the category of cones. And these are the sorts of things that we're going to look at later, these various steps in dimension 2, and try to see what does and doesn't work. But this is how it works in dimension 1. So, any questions on that? All right, if not, here is the question for the talk. What does this look like in dimension 2? And to answer that, we're going to have to go through everything we just said and work out what it means to put a 2 in front of that. And some of these things I'm not going to think too carefully about, but others I think are worth looking at, and we'll go through that one step at a time. All right, any thoughts before we move on? Nope, okay. So this brings us to 2D background. What time did we start, by the way? About 22, is that right? Okay. Good. So here's my amazing definition of what a 2 category is. So a 2 category, I hope you're ready, is a place where we have objects which we draw as labeled points. Maybe we forget the dot. We have morphisms. And we have morphisms between our morphisms because we weren't previously satisfied. And I have no idea which way is left to right or up to down, so please forgive my arrow drawing. And these things can be glued along any boundary that they share, and there are identities in every dimension, and everything works strictly and wonderfully, and we never have to worry about anything. My favorite example of a two-category is cat, and it's a pretty good place. So here, the objects are categories, the morphisms are functors, and the two morphisms are natural transformations. Yes.
So is the two-category the category which is the cat?
Yes. Absolutely. If you know that, then yes, that makes this much easier. Yeah. Another example is any ordinary category, so a one category, where these things are only identities. So they only exist if the two ordinary morphisms are the same, then there's an identity, otherwise not. And various things in between. Yada, yada, yada. So these are very nice and strict, but the world is a cruel place, and morphisms of two categories are not so nice and strict. And while we can, as an accident of dimensionality, get away with considering very strict category objects, we cannot do anything about the morphisms. And so here's this very scary word, a pseudofunctor. Between two categories. This is going to be like an ordinary functor in that it's going to send like types to like types, by which I mean is a mapping of objects of C to objects of D, morphisms of C to morphisms of D, and two morphisms of C to two morphisms of D, okay, such that domains and codomains are respected and so on. But it's not required to respect the composition operation at the one-dimensional level. What do I mean by that? I mean, if we had a diagram like this in C, then by applying F to this, we have one of two choices. We could apply F to each part. Sorry, there should be F's over here. Or we could apply F to the composite. Ordinarily, a functor would make these two things equal, but a pseudofunctor only makes these things isomorphic with an invertible two morphism. And there are just a bajillion laws about this, and I'm not going to say anything about that, except point you to what I think is a great and also the unique reference on two categorical stuff. That is the book of Johnson and Yao, and it's called Two-Dimensional Categories. If you'd like to know more. Any questions about pseudofunctors? We don't need more of an understanding than this. I'm going to keep this up. But I'm not done torturing you. We also have a version of natural transformations. And I'm going to say even less about this one. So a pseudo-natural transformation is like a natural transformation, but instead of the squares being required to commute exactly, we now insert more invertible stuff. So a pseudo-natural transformation between pseudo-functors is the sorts of stuff that we're used to and if I put an equals in there, that kind of looks like a natural transformation, but I don't. I put an invertible two-cell instead. And this, again, obeys a bunch of laws, but that's good enough. So these are the sorts of higher dimensional natural transformations, and we have some terminology. So if alpha f is in fact the identity, then this is called two natural. And you should think of that as the adjective TOO. It's way too natural. And this doesn't happen. And if alpha f is not invertible, then you're doing something wrong. And this is called lax natural. I have strong feelings about this. All right. And not content to end the misery there, there are things called modifications. And I'm going to tell you absolutely nothing about them. So this is a great definition. A modification is something that lives between pseudo-natural transformations. So this is like how in dimension 1 we had functors and discovered a new dimension of natural transformations. So in dimension 2 we have functors and natural transformations, and we get a new dimension for free, modifications. No comment on that. Any questions about all the stuff that I've very quickly run through? All right, so let's probe for the existence of such a theorem by looking at the connecting thing that I highlighted earlier. The thing that we're going to compare very specifically now, once I give you meaning to this, is 2D limits versus 2D terminal objects in some 2D category of cones. And the reason that this probes for something like this is because this was the crucial step in that list that I've erased, unfortunately, that related limits were related to representations some purely formal way. Then representations were related to initial or terminal objects in the category of elements, and the category of elements of something was purely the category of cones in some formal way. So the only place that this could really fail is in this step, and that's why we're probing it by doing this sort of thing. All right, and this brings us to too many cooks. So unfortunately, we're going to have to go through the sentence and say what we mean for each one of these words. But I'm only going to do that kind of lightly, so that we don't spend too much time on this, but give you an idea of the sorts of choices we can make in giving these various things meaning. So the first one I'm going to say is, what should a two-dimensional limit be? And this one, we have several choices. So if this is a pseudo-functor, and we take an object of C as well as something to F, okay? And for the time being, we're going to take this as a pseudo-natural transformation. Then we can ask for this same map to, I guess, pseudo-natural transformations. I think I've been spelling. Let's just do PS. I don't have to guess which vowel comes after that. So by this, I mean pseudo-natural transformations between this thing and this thing, but also modifications, because surprise, this is now a category. Before it was a set, but now we're in dimension 2, so this thing becomes a category. And we're going to ask for this to be, at first, the kind of weakest thing we can do, an equivalence. This thing is a category because we were in a 2 category, so we have morphisms as our object and 2 morphisms as our morphisms. And this thing is a category because we have pseudo-functors as our objects, pseudo-natural transformations as our objects and modifications as our morphisms. And so we can ask for these things to be equivalent. And if we do all of this, we'll end up with something that is called a bilimit.
The L is a bilimit.
Yeah. But we made many choices in this. We could instead take two natural transformations as our objects over here. Or we could ask for this to be an isomorphism. So there's some room. And then we have to work out, so kind of that's this part that we just gave some meaning to. And then we have to work out, what do we mean by all of this? Well, we can do it in analogy with the stuff we've done before. So one thing that I might say is, this doesn't, to my knowledge, have a name in the literature, so I'm just going to call it pseudoterminal for the time being. And we could say that a pseudoterminal object is when we have an equivalence of the harms to the terminal category instead of an isomorphism.
What would happen if you used this as I to be empty?
Sure. So if I is empty, then what is this thing over here? So this has objects, pseudo-natural transformations between delta C from empty into C, and also F. And a pseudo-natural transformation is indexed by the data of the objects of this category. So there's just a unique one. So this turns out to be terminal, the terminal category. And by asking for this to be an equivalence, we recover this thing. But so I don't know how many quotation marks to put around this. There are a lot of, this isn't well-trodden ground, and there are many choices we could make, but let's just call this pseudo-terminal for the time being. Even though I said this is a bilimit. I don't want to call this biterminal. Right. Yeah, I don't know which way around to do this. How about now? Okay, and then the last thing we need to, so that's this thingy over here that I've said, and then we need to kind of work out what the 2D category of two-dimensional cones is. And again, we have an abundance of choices. But we could form several kinds of pullbacks over here. Sorry, this is in the one category of two categories and whatever our favorite and pseudofunctors. So, right, I'll annotate this in a second. I guess this is one. No. Which way around is this supposed to go? So we choose some adjective over here, and we want this is from Oh, I'm doing this at the wrong level, I think. Which adjective did I want? Oh boy. So I think this is the square which happens in the one category of two cats and pseudofunctors. Does this compute the right thing? I think so. Right, so this is now where we get to make far too many choices. So one way to do this is to take pseudo everywhere. And if, sorry? This and this are the cooks, yeah. So what is this thing constructing? I'll tell you over here. This is what we, as written, this is kind of the pseudo slice 2 category of cones. So the objects of this thing are supposed to be pairs, objects of C, and pseudo-natural transformations like so. The morphisms are supposed to be things like this. I don't know which way this goes. With an invertible modification in the middle. So it would have been commuting triangles, but because we chose PS out here, somehow this picks up this extra piece of data. I'm not going to tell you what the two morphisms are. It's like some pasting thing over here. Yeah, exactly. But we have lots of choices. And so the cones are pseudo-natural, as I've written them. And we could ask for these things to be invertible, or just, you know, any old modification, or we could ask for them to be 3 qualities. You know, we have many choices over here. We have many choices over here. Sorry, here. And the question is, do any of these things ever line up, right? Is there some theorem that says, for instance, a bilimit is pseudoterminal in the pseudo-slice category of pseudocones? No, that one doesn't work. Okay. Well, what happens if we make everything maximally strict? If we take the cones to be 2 natural transformations, and we take this to be an isomorphism, so we get 2 terminal objects, and we take everything here to be as strict as possible, so these triangles commute, is a 2 limit, a 2 terminal object in the 2 slice category of 2 cones? No. Okay, maybe we're not detecting enough data, so let's throw in tons more by forgetting that these are invertible, and take lax and just mix and match things. All these theorems are false, every single one of them. And you can find out details about this in our paper, 2 limits, and what's it called? 2 limits and 2 terminal objects are 2 different. This is joint work with Lynn Moser, a friend and colleague of mine. In fact, all of this, thanks, is joint work with Lynn. It started at MSRI.
When you say they're 2 different, is that only a time, or are they different?
So there is one true implication.
Okay.
There is one true thing, which is that 2 limits will be 2 terminal in the 2 category of 2 cones. So if if you line up things correctly, if the type of cones, if the strictness of cones and the types of terminality agree and the stars align, then being a whatever kind of limit is strong enough to imply the correct kind of terminality in the correct kind of place. But if the stars don't align, then they're just completely independent concepts.
There's no map either.
There is no map either way. There is, I mean, at the level of lax, which I hope is repugnant to everyone in this room, like, you're just detecting, asking different questions completely. Like, lax limits somehow completely unrelated to lax terminal objects or lax cones or any of these other things. And in this paper, we have counterexamples for all of these things, and they're all, except one, they're all finite. So, in fact, fit within the confines of a standard US letter page. And the one that is infinite is freely generated by two morphisms. So these are very, very small somehow. And the counterexamples to all of these conjectures. And I guess the point I'm making is, I want to encourage you, when you come up against something in two-category theory, to just check it, I guess. Start drawing things and see, well, this must compose to that. And I know it seems like there's a lot of things going on, but we're free to pick the diagram shape. And we're free to pick the kind of terminality that we want. And if you start doodling, you'll find these counterexamples for yourself. Yeah, any questions about that?
There's no like best one, or if you use weighted limits or something that everything's good, or any less, no morality, no moral here except there's lots of cooks.
There are too many cooks is the only moral. But we've determined something I think pretty important by doing things this way around, which is that it looks like this has failed, but to spoil a bit, because apparently I plan talks that are way too long. To spoil a bit, the issue here is this thing. It's not that there isn't a representation theorem. There is. It's very nice. But the issue is somehow that by forming the ordinary category of elements thing, even for a pseudo-functor, we just miss way too much information. And we have to change that. And if we do change that, we can say that a pseudo-limit or a bi-limit is pseudo-terminal in something or other. And I'll make that precise in a bit. So there is a theorem like this. But it's just not these ones. And it's some weird coincidence of low dimension that the ordinary category of elements construction captures enough data.
I mean, was part of the problem that you were taking strict pullback there? Is that still a little bit?
Oh, I mean, so the strictness of this pullback is kind of not at issue here. The strictness of this pullback, I guess, what would that change? If this didn't commute, but instead there was an isomorphism in here, I guess that'd be bad. That's just not a category of cones anymore, somehow. It's like we would have an object as well as an object in C as well as a pseudo-natural transformation like this, whose domain was isomorphic to this thing and whose codomain was isomorphic to this thing by pseudo-natural transformations. It's just not, it's not adding the sorts of stuff we're interested in over here. But that's a fair question. Yeah.
I'm not sure because it's at 2 level, but I think that second map there is some sort of isocollaboration. So that this is equivalent to that. So as long as everything is expressed at a loose level of equivalence, it should change the counterexamples at the fully level.
I mean, maybe, but I want to emphasize that we can reach counterexamples purely one categorically. We don't have to worry about equivalences or isomorphisms in here or anything like that. I mean, what you're saying is probably true, but this really replicates what we want, the ordinary one categorical pullback. Namely, objects are cones, morphisms are triangles with some amount of data, and the two morphisms are something that they should be. And the issue somehow is not that this is a one categorical pullback. The issue is somehow that this is not the right place to look for limits. Which brings us to the question, where is the right place to look for limits? And this is section 4. And this is where we observe that 2 times 1 is 2. And it just occurred to me that 4 minus 2 times 1 is also 2. So this is a very true section heading. Okay, so does this mean that there's no representation theorem? And recall that we said that we had this chain of reasoning, that this is a limit if and only if this is a representation of, in the one categorical case, this thing, if and only if this is initial somewhere, if and only if this is terminal somewhere. Okay, this was our chain of reasoning in dimension 1. And we've gone ahead and we've snuck various adjectives in here, like by, or, I mean, I haven't told you this yet, but implicit in this was some kind of two-dimensional representation idea. And we spoke about the different kinds of terminality. So Lynn and I decided, well, let's check these things. Which of these are formal, which of these are not? So it turns out this is still true. This was completely formal somehow and didn't change as long as these adjectives line up correctly. We don't want to mix and match things like by limits or lax representation. Doesn't mean much. But if we align the types, then this all works out. So that's great. I'm going to inconspicuously move to the other end of the diagram. This is also completely formal. This is some computation about the category of elements of some giant thing, and that's like take pullbacks for 3 days and everything works out. This turned out to be the problem. Unfortunately, this is the representation theorem. So we have to replace this link in the chain, and everything else should kind of fall into place. What should this link be? Well, work of others, let's say Verity comes to mind, Grandis, Perret, and some others, pointed to a yet wider future of double categories. And double categories seem to solve a bunch of problems. They also create a bunch of problems, as some in the audience might attest to. But they definitely solve problems. And it was kind of somewhere between known and suggested that double categories would provide an appropriate representation theorem. I say somewhere between known and suggested because it wasn't written down anywhere. And when we showed it to people, they said, yes, of course. So I don't know what that means, but I like to imagine all of these people knew this but didn't write it down. And so I need to tell you what a double category is, maybe very quickly. So a double category, which I will try to remember to indicate with double struck letters, is a place where we have objects, we have horizontal morphisms, we have vertical morphisms, and if this isn't your preferred orientation, I apologize. And we also have two-dimensional things, which I'm going to call squares. And I don't know how to label things. Like that. And we have enough identities to make your eyes soar, and we can glue squares along common boundaries and stuff like this, and it forms a category this way and a category this way, and various associativity properties hold. And a reference for this kind of stuff that I am not going to say too much about this. Grandis has a book, High Dimensional Cats. I mean, the title's Categories. That probably tells you, oh, that certainly tells you everything you need to know about double categories. So just like for two categories, we had, pseudo-functors. We have these horrible things for double categories as well, horizontally pseudo-double functors and horizontal pseudo-natural transformations and all this other stuff. But the thing that I want to emphasize is that if we give these words the appropriate meaning, we can in fact prove this theorem. So this is joined with Lin. So given a pseudo-functor, so I haven't told you what a birepresentation is, and I'll say that in a little bit, but it turns out that we can prove a very strong analog of this. So there is a birepresentation, rho C blank I, so an ordinary representation is a natural isomorphism, but a birepresentation is a pseudo-natural adjoint equivalence. It's a mouthful, but it's the natural high dimensional weakening of this. And the other thing that is true is that there is a, I guess I want to write it the same way, there is a double bi-initial object II in the double category of elements of F. And lo and behold, we have a representation theorem. I want to say that this is defined as a pullback in the one category. So it's not too terrible to understand what this is and work with it, but I'm not going to think too carefully about that. And this is pretty nice, but unfortunately it's placed us squarely in the land of two categories, of double categories. So is there a two-categorical version of this? And so I think our biggest contribution to this is the answer yes. And I will briefly make an indication about what that looks like. So there is a kind of classical functor from double categories to two categories, which sends a double category to its horizontal category. So I mentioned briefly over here that part of the dart of a double category is horizontal morphisms and identities, and those compose and so on. And so this thing extracts the horizontal two category. We could have chosen the vertical two category, but kind of that's not of interest. But there's another one, and this is the one that is new and improved, which we call V, just to be confusing about things. And this does something I think pretty interesting. So this, on a double category, gives us a two category whose objects are the vertical morphisms of the double category, whose morphisms are the squares and whose two morphisms are something. I don't want to tell you. It's a commutation conditional. It's the data of more squares and something about vertical composition. And it turns out that between these two things, we detect almost everything about a double category except for vertical composition. So we lose some amount of information. But luckily, there is nothing interesting going on over here in vertical composition. And so the theorem that we can prove almost. So the two morphisms, I guess. So suppose we had two parallel one morphisms, by which I mean two squares between this and this. Then a two morphism is the data of a square that lives above here, whose vertical things are identities, and a square that lives below the other one, whose vertical things are identities, such that they compose to be the same thing. It's, you should think of this as a commuting square of two cells, which is what it is, somehow. All right, so to wrap things up, we managed to show...
Double category starting,
yeah, just like the two categories are strict. But the morphisms are really lax, and that's good enough. So we managed to show this thing, that if we have an object that is double bi-initial, which I haven't told you what it means, this is the same thing as I is bi-initial in the horizontal one, but not alone, and the vertical identity on I is bi-initial in VA. But most importantly, this last condition is in fact enough.
The TFA thing?
Yeah, sorry, thanks. So it turns out, so we can say what double bi-initial is in the world of two categories, if it's bi-initial in this two category and bi-initial in this two category. But it turns out this is good enough, and this is the condition. So we can apply this to this, and kind of the finale over here is the corollary. Calling it a corollary is a bit unfair because there's a bunch of work that has to go in to show that certain functors commute with constructing elements and things, but they do. And the final thing that I want to leave with is this. So there is a bi-representation II is bi-initial in H of the double, I don't know how to write it, lowercase double struck E, which turns out to be the ordinary two category of elements. which is some theorem we can show. And I, identity on I, is bi-initial in V of this thing, which we call the category of morphisms of F, or just that last condition. And there's our representation theorem. So it's possible, in fact, to define these things completely two-categorically without ever mentioning double categories, and it's possible to completely inline all this double categorical stuff to just prove this in the world of two categories. You probably wouldn't want to do that, because it turns out there's yet a more general thing that implies this theorem. But the summary is, if we want to look for bi-representations, elements are not enough. We need to look at morphisms. We form something whose objects are morphisms in each category instead of just objects, and then that's good enough to detect bi-representations, good enough to detect all kinds of two-dimensional limits. And that's the summary.
Do you think of this as you've proven that the category of elements doesn't work, but this other thing does work? Or do you think of it as we've corrected the category of elements, it's really this thing? Like what you thought was the category of elements just happens to be it for one dimension, but the definition doesn't generalize, you would do with this instead.
No, I think this doesn't generalize either. And so we've managed to correct the category of elements for dimension 2. And I think, not having worked too carefully on this, if we wanted to move to higher dimensions yet, we would have to work way harder than this. So this, I wouldn't advocate for this being the category of elements. I would advocate for this being a useful computational tool in dimension 2. Although, yeah, again, there are no theorems about the category of elements. It just so happens.
One way to get the what am I going to say? If I have an object in a category, then I can factor that as a final followed by a speed up vibration. There's a factorization system on cat where you can, where it's either initial or co-final or final or something followed by a speed up vibration.
Okay.
And if you do that for the object you pick in C, the function from the terminal up to C given by that object and factor it, you get that representable its category of elements. Get its category of elements. I'm not sure if I'm going to say anything interesting or not. I know what I'm going to say. Can category of elements be replaced by some kind of factorization system on two categories? And that could be what's going on? Sorry, that's okay.
No, I think that's a really interesting question. But here's some blind speculation. I think factorization systems are not high enough dimensional. And I think the one category of two categories is not a good place to look for these kinds of things. And it turns out that there's no two category of two categories, at least the way we're thinking about it. Pseudo-functors and pseudo-natural transformations don't form a bicategory even. And so I think that this is deep water, and I'm not sure what the right answer for an analog of a factorization system would be, because the next best thing is a tricategory of two categories. Maybe. So behind the curtain, this is actually a result about trivial fibrations, which I didn't get to. The definition of double bi-initial is that the projection from a double slice is a certain double trivial fibration. And the result is that these two jointly preserve and reflect trivial fibrations, but this is a retract of this. So in fact, this is all we need to look at for trivial fibrations. That's the real theorem somehow of this paper, and everything else is loads of applications of that to all these things. So I could believe that weak factorization systems with enough carefully thought out properties work, but trivial fibrations, the way we define them, only work for strict functors. And it turns out that the projection is a strict two-functor or a strict double functor out of the slice. And so how we do that for general pseudo-functors, I don't know. Interesting question. If you want to know more about that, this is really not my wheelhouse, and I direct you to the I forget the title of the paper, but my co-author Sarazola and Verdugo put a model structure, I think it's something like this, a model structure on double categories that is somehow compatible with the lack model structure on two categories. And that's the inspiration for the way we prove that.
Thanks, Bill, once again.